Welcome, everybody. Fantastic response to our second COVID-inspired stay-at-home webinar on construction history topics. Sorry for the change in links for the webinar. We call this called a defensive technology shift, okay? I also want to extend a special welcome to a bunch of students from the University of Maryland who were tasked with watching this video as part of their class. So just so speakers, so you know that, as well as some of my students from the University of Minnesota. So let's move on to some of our historical shifts. I am Peter Hilger, president of the Construction History Society and host of this webinar as faculty director of the Construction Management Program at the University of Minnesota, with a passionate interest in all things history. I'm joined today by my colleague, Mr. Clifton Fordham of Temple University. You can wave, Clifton, it's okay. There you go. From Temple University, who will serve as moderator and present your questions. So please use the Q&A button at the bottom of your Zoom rail to enter your questions. We will take questions at the end of all three presentations, and we can go past our appointed time, but we may insert one or two questions while we make our speaker transitions. Also, if you are having any technical issues, you're free to use the chat box as well. We're also joined by Melanie Fierce, the Executive Director of the Society, to whom you can also address questions about membership in our society, which we hope you will become, and anything else of such interest. She will communicate after the fact about connecting to our recording, which we will eventually host on our website. I'm also joined today by speakers, excuse me, who will address your insatiable need for history. I will let them expand on their personal introductions when they present, but we'll start off with Miss Rebecca Kennedy. She's an architectural historian, freshly back from Oaxaca, Mexico, where she has been studying her craft of traditional construction. We are joined as well by Mr. Kevin Griebenow, a civil engineer with the Federal Energy Regulatory Commission, and what I understand, a pretty damn good presentation on masonry dams. And finally, by Mr. Paolo Vitti, hailing from Rome, Italy, also a visiting faculty with Purdue University to talk about the origins of brick vaults. So with that, let's vault over to Ms. Kennedy to get us started.
Hi, everyone. Thank you so much for having me. I'm very excited to be here. So I graduated from UT Austin studying architecture about a year and a half ago. I'm currently work at HHM, which is a preservation consulting firm here in Austin. But I'm going to present about my independent research that I started in my master's program, which is looking at traditional construction techniques in southern Mexico, specifically in the state of Oaxaca. And beyond looking at those construction techniques, today I'm going to share with you a little bit about a new path I've been going down, which is looking at the ways that those construction techniques and subsequent changes to more modern construction techniques are altering the physical landscape of the towns that I study. Let's see, it won't go to the next slide. There we go. So just for some background information, Oaxaca is one of the southernmost states in Mexico. And when people think of traditional construction, especially in Mexico, they automatically think of adobe. But part of my passion is disrupting that narrative. There are a myriad of construction techniques in Oaxaca and throughout Mexico. And sometimes they can be as specific as a certain town, or if not, a cluster of towns, a small region might have its own construction technique. And often those techniques are variants of broader techniques, like even, global techniques like wattle and daub or coursed earth or cob. But I find these ways of building very interesting because they're these little microcosms of how culture and the environment are really working together to create a construction technique and a sometimes a variety of construction techniques in a single town. So when I'm thinking about the ways that these techniques have impact on the broader land use patterns of, these are, by the way, these are all techniques that I study in very rural areas. Urban areas have primarily shifted to fully concrete, but some of these examples are still extant in small towns. So one of the sort of anecdotes that always comes to mind is the story of zacate, which is a type of grass that used to be used for thatching roofs. This photograph was taken in the town of Zacatepec. The first part of that town's name is zacate, that grass, because all of the roofs in the town used to be made of zacate, and it used to grow in abundance in the public lands surrounding that town. And this photograph was taken, these two people kindly agreed to take me out to where the zacate fields used to be located and where people harvested the grass from. And today there's only some like scattered plants, very poor quality. They wouldn't be good enough for thatching with. And these people also we knew generally where it was, but there's sort of a loss of knowledge of where the plant was even, where it's located, where those fields used to be. So this shift in abundance of the plant and of local knowledge has to do with widespread adoption of concrete construction and corrugated metal roofing, which of course has been sort of marketed as this indestructible building material. But roofs like the one on the left that were thatched used to, as I mentioned, those used to be literally the only roofing technique in the town. And using that material went along with a certain set of practices of sort of land stewardship, such as burning the zacate fields every year, and also just the act of cutting the grass to use for thatch the cutting and the burning both stimulated regrowth of those zacate plants. So as building techniques have shifted to concrete, the plant itself has ceased to reproduce. So I just find this story very indicative of trends that are happening in towns all over Oaxaca, all over Mexico, and all over the globe, where two interesting things. So the younger generation really has no knowledge of where those plants were located, how to harvest them when they might be ready to harvest, let alone how to build a building out of them. And secondly, even if they wanted to, the materials, I mean, mineral resources are a different story, but biological, like if we're talking about plants, there isn't enough abundance to really build with. Two architects tried to build a house in Zacatepec 2 years ago with a zacate roof, and there literally wasn't enough quality grass in the whole town to thatch one roof with. So things like this building construction store that's sort of nostalgically called zacate, and you can see the only product for sale is concrete block. So that's kind of typical. Not that they would have sold zacate in a store to begin with, so it's kind of doubly ironic. So I'm gonna sort of go all over Oaxaca, so pardon me as I travel around. When we talk about what those processes of material harvest and production looked like, they involved a really in-depth knowledge of local plant species, where they were located. For instance, in this photograph, they're refining agave flower stalks to use for wood as purlins. And in the case of agave, you had to know exactly what species was right for the strongest quality wood, as opposed to things you might use to make alcohol with, or there's a myriad of uses for agave. And then when the plant was going to be in flower, what time of year, and then you had to know specifically when the flower stalk was half in flower and half in bud, and that's when the wood is supposedly the strongest, and they also harvested by the moon. So these construction materials involved really extensive knowledge of the location and all kinds of information about local plants. and then how to refine them into a finished building product. So I'm going to take you guys through the sort of full process of material harvest and refinement for log cabins, which are really prevalent in sort of northwestern Oaxaca in a really heavily forested region where virtually all of the, well, aside from adobe, all of the building techniques are very reliant on pine products. So when people are deciding what technique to build with and sort of doing the calculus of what for us might be saving to build a house, saving money, sort of the cost of a traditional home depended a lot on the distance that you had to travel to gather a material and the way that the means of transport. For instance, pine needles, which people also used for thatch in this area, are a relatively cheap material because you can carry them on your back. You can sort of like enlist your family over a period of days or months to help you harvest and carry it. And then a material like logs is a quite expensive material because you need help processing the logs, which involves trade of labor with someone in your town from a friend or a family member, which you have to pay back that labor with help on future projects. And all of these techniques were outside of a wage and based on sort of cooperative systems of labor. And then it also, with logs, it also entails use of oxen to drag the logs because they're very heavy. And to have oxen, you're automatically sort of wealthy because you can afford to have them. And, or if you're trading them, trading someone else for use of their oxen, that's, again, increasing the cost. So these types of decisions that involve sort of the landscape were very integral to deciding which materials to use and what materials you would choose to build your house out of. So supposing that someone does decide to build with logs, you would go into the forest typically in pairs of two and work with a partner to cut down the tree and process it, basically peeling the bark off of the tree, working alongside sort of opposite someone else. And you end up with an octagonal log, as symmetrical as possible. And they're like very measured about making it symmetrical and all faces even so that it will sit nicely in the wall of the building once you're using it for construction. And then they leave it sit in a forest for a minimum of 2 weeks to dry out so that it's lighter to carry. And at that point, they cut notches or holes in the end of the log so that oxen can pull it. Typically, this is where trade comes in handy because you might enlist someone else and their oxen so that you have two pairs carrying as much lumber as possible back so that you can get the whole job done quickly. And on the left, a lot of houses still have holes left over from dragging the logs back to the building site from the forest. And then just really quickly, in the same region, split shakes were also very prominent roofing materials, and using the exact same, pine products in this region entail a bunch of different sets of knowledge that varies very much based on what the finished product you're looking for is. So with split shakes, you need to cut the tree open, cut a little incision to check the grain pattern and make sure that it's straight enough grain so that it will split evenly into nice shakes. So these guys, which trees they've checked before, which trees might be coming of age for kind of more old growth lumber forests like the back of their hand. And I think the split shakes are an interesting example of sort of how these construction techniques still have, even though they're hardly used today, although they are somewhat, how have left their mark on the broader landscape. In this photo, this is another town where they used to use split shakes extensively. And here in the photo, Carlos is showing me like one of the oldest trees that he knows of in the entire town. And the reason that it's still standing is because it essentially didn't make the cut for the split shakes because it didn't have a grain pattern. And the rest of the forest is starting to grow back around it. A lot of it's sort of poor quality wood, like you see after extensive harvesting. But the oldest trees are the ones that basically weren't satisfactory for split shakes. And these changes in harvest, also related to agriculture, of course, but very much related to construction as well, are starting to have sort of interesting impacts on as places become more urbanized. We sort of would expect that the surrounding areas would become less vegetated, but in fact, the opposite is occurring. And as people use the landscape around their town, less for agricultural cultivation and less for cultivation of construction materials, the town landscape is in some ways sort of becoming more neglected, and as a result, growing back, which of course has some ecological benefits potentially, but it's also interesting because it implies sort of a lack of stewardship. So these changes in the physical composition of the landscape also are related to our sort of conceptions of the outdoors and nature, what we might call nature. This is a drawing that a high school student made of sort of what his favorite place in his town was. And he described the forest as basically made to relax in, which is a totally different concept of the outdoors than his grandparents would have had, seeing it as, of course, appreciating it in so many ways, but also as primarily a place of production and labor, and sometimes backbreaking labor. His parents sort of coming of age in the generation where the shift to the wage economy was happening, like I'm generalizing here, but have a more nostalgic view of nature. And then the youngest generation today just has a much more sort of urban conception of nature as a place for recreation. So kind of bringing this back to construction materials, Oaxaca sort of, and many parts of the globe are witnessing this really dramatic transition in construction technology that's almost completely taken place. And again, it's hard to know times whether importing materials and potentially having regrowth of forests, if that's a good thing, or whether it's better to have a really innate understanding of resources and how they're being used. These are complicated decisions, but I think it's important to analyze the ways we often think of materials and construction technique as a really direct relationship. If we have X material, then that leads to Y construction technique. But I think these towns offer a really interesting perspective in sort of how we get to that place, how we shift from construction material to another, and how those transitions are, sometimes have negative consequences or positive, but in this case, sort of negative consequences that go beyond just buildings themselves, but are actually impacting and also impacted by much greater social, cultural, and economic narratives. So these shifts in construction technique are impacting the landscape, impacting people's conceptualization of kind of the landscape and a broader worldview. And as they change, they sort of contribute to the obsolescence of these construction techniques. They become almost longer viable and almost impossible to build with under certain circumstances. And we think of these things as sort of just taken for granted, but it's interesting to see how it's actually playing out in a specific place. So thank you guys very much. I'm looking forward to the next two presenters. I will stop sharing my screen.
While Kevin is getting his setup going, Rebecca, just a quick question. How did you find out any information about how well that type of construction fares in what is likely a pretty significant seismic zone?
Yeah, all of the construction techniques that I study are so influenced by I mean, it's an incredibly seismic zone. And almost all of the connections on these building techniques are, there's a lot of notching, a lot of lashing, a lot of attention to foundations. So yeah, they've all evolved with very much that big part of the equation. Yeah.
Good. All right, Kevin, I understand you're unmuted now, so give us a damn presentation, will you?
All right, thank you. Thank you, Peter. Yes, I am a dam civil engineer, just to continue that thread. Thank you for having me. And I just want to start out, I've been involved with dams for more than 25 years, and I too have found history, in this case, the history of dam and dam design, very interesting, especially when it comes to one of the forces acting on dams, uplift pressure. Just in a general sense, I find interesting about dams, or a dam statistic, is that we here in the United States have built a dam every day since our independence in 1776. And just a little caveat or disclaimer, my view should not be taken or misconstrued as a Federal Energy Regulatory Commission policy. All right, so my trip down memory lane, or the history of dams, starts with this book, which is available for free on the internet. You can download the PDF. And when I was reading this chapter, I realized how little I knew about the history of dams. And so it led me down this road to explore the assumptions, design, and construction of dams, and followed by their failure. And as I had said, the main design assumption I will be focusing on will be the uplift pressure on the base of dams. But first, I want to start out with a thought experiment proposed by Henry Petrosky, a professor of civil engineering and history at Duke. And if you haven't read any of his books, I highly encourage it. He's written numerous books on engineering and design. So his thought experiment deals with the Titanic. And Titanic was the largest ship in service, and with its sister ship, the Olympic, they were declared, quote, "As far as possible to do, these two wonderful vessels are designed to be unsinkable," close quote. Well, we know that on the fourth day of its maiden voyage across the Atlantic, the Titanic sank after hitting an iceberg. More than 1,500 people died due to the failed design, human factors, and the assumptions built into the lifeboat system. So Professor Petrosky asked the thought experiment, what if the Titanic had made its maiden voyage and many more successful voyages? It is likely the shipping world and naval designers would have copied and, quote, improved on this successful design, and over time reducing the lifeboat and safety systems on board as thought to be unnecessary. And in recent times, the design of the 737 MAX airplane comes to mind with this thought experiment. In his book, his conclusion is that, quote, successful design and change comes not from emulating success and trying to better it, but from learning from and anticipating failure, whether we actually experienced or hypothetically imagined, close quote. With this in mind, let's look at the design and construction and failure of a few dams. And one dam I like to start out with is the Marab Dam, which you can find on Google Maps. And I like this dam because I was a Peace Corps volunteer quite a few years ago in the country of Yemen. And the Marab Dam was initially constructed about 3,500 years ago, and its final height over time was about 60 feet high. It also might be the first recorded dam failure, as in the Quran, it notes that the dam breached in about 570 or 575. Of interest to this group, a paper presented at the International Congress on Construction History in 2003, researchers found 72 dams from Roman era constructed in Spain from the 1st to the 4th centuries. Many of these dams are masonry and still in use. So the Romans were not only did arches and roads, but they also did some amazing dams. And also related to this, in 1586, Simon Stevin and Mr. Pascal in 1663 solved the hydrostatic paradox demonstrated by Pascal with the exploding barrel experiment. And if you have not Googled this, it's a great YouTube video of the exploding barrel experiment. That is, the pressure at a certain level in a fluid is proportional to the vertical distance to the surface, not the volume above it. So when you look at that YouTube video, that will make more sense. However, this understanding or finding does not translate into an economical or scientific base shape for dams for about another 400 years, or about 1850. So this dam is located in Western France, the Griebenow Dam, and it was a masonry dam built in the 1800s. And note the water is on the right side of the section and the downstream face is vertical. In Edward Wigman's 1888 first edition, The Design and Construction of Dams, which I would say was the Bible of dam construction at the time, he states, quote, "The dam shows an utter absence of any rational theory regarding the proper method for designing a masonry dam," close quote. I don't know if I'd want to be that design engineer and put that on your resume. However, the dam exists today, and it's interesting, it's used as a climbing wall. You can see the red little dot there on the wall, and that's actually someone using it. And another similar dam is the Griebenow Dam in eastern France, and it was initially built like the Griebenow Dam with a vertical downstream face. It is mentioned in the ASE book on instrumentation for dams in that the crest was surveyed to monitor its displacement. This monitoring during successful infilling and emptying found the dam to be deforming elastically. With movement mentioned beyond what was expected, counterforts or braces were constructed against the downstream face. So just a gravity dam, which we hear a lot about, is constructed of concrete or masonry and is designed to hold water by using the weight of the material to resist the horizontal force of water. The previous two examples were poor examples of a gravity dam. A design for a gravity dam is finally resolved into an economical design in about the mid-1800s. An early design is by the Frenchman Sazali. He believes that an economical design for dams would eliminate tension in these masonry walls. To me, it's interesting that they were thought of as masonry walls and not really as a dam. But there no uplift pressure was acting on the base of the dam. And notice that with his assumptions, the base is basically or maybe slightly less than the height of the dam. So 8 years after he comes up with this theory, a very risky engineer, I would think, implements that theory and constructs or designs and constructs the Furens Dam in France. And so he builds the highest dam in the world at the time with this new theory. And that just seems a little strange to me to way to test out a new theory. The 180-foot high dam was completed in 1866 using 52,000 cubic yards of masonry. As the method was new, the dam was slightly arched across the gorge for additional strength. And again, in Wegman's first edition in 1888, it is said to be the first masonry dam, quote, built according to scientific principles. And again, the dam is still in use today for flood control. 20 years after Sazali's profile of equal resistance, the famous Scot William Rankin develops 3 rules to ensure the stability of dams. The second rule, again, deals with tension, and he says it should be eliminated in dams by keeping the resultant in the middle third of the base or the kern. And again, uplift pressure is missing, but directly impacts his rule number 3. So anybody that's played the game Jenga, where the blocks are precisely a third of the total width of the column, are related to this. This series of figures shows why with just a little unbalanced loading in your Jenga tower makes it falls over. As the eccentricity of the load increases, it changes the stress at the base of the block. Note in figure C, with the load at the edge of the middle third, there is no stress at the opposite end of the base. And as that load moves to the outside of the middle third, tension forms on the opposite face. And that's assuming the material can handle these tensile forces. If not, it will rotate over and your Jenga tower falls over. Now, to me, it's interesting. I started out in architecture, but ended up in civil engineering. And I see these, and the pinnacles and these flying buttresses in 1472. And why is that included here? Because to me, it shows that these masons in 1472 know that these pinnacles reduced or eliminated the outward thrust coming from the flying buttresses and reduced the tension in the piers in these cathedrals. As we will see, this realization to reduce or eliminate tension is not codified in dams for another 400 years. Now it gets interesting. Belgian engineers are concerned about this uplift pressure, and they called it a novel force for their, again, about 160-foot high dam. This enormous cross-section of this arch gravity masonry dam was due to the assumption of uplift pressure. The design assumption of the masonry being totally submerged generated a base of 66 meters, 130% greater than its height of 50 meters. Upon first filling and for about 4 years, the leakage rate through the masonry was about 220 gallons per minute, and some thought that leakage through the masonry was good. Also, what was very interesting is this masonry dam took 6 years to build with about 325,000 cubic yards of masonry. The work per man amounted to about 3 cubic yards a day, and in today's construction, I don't know if that would cut it. Similar to the pinnacles on top of the flying buttresses, were the engineers thinking to include this 300 tons of the 44-foot tall lion sculpture in the stability and stresses in the dam? I don't know. And if you think about it, this 300-ton statue is very similar to a post-tension anchor that we install through dams to increase their stability today. So now we move to Great Britain, and there is a Welsh dam, Vyrnwy. This dam is of Cyclopean rubble, and it's very similar to the massive Gillespie Dam 15 years earlier, and is the first large storage reservoir to supply water to Liverpool. Its base is about 90% of the height. And notice the static computation for locating the resultant, and that it is located within the middle third. However, this dam has a new twist. It has drains. And I've read before that the drains were installed at the insistence on the contractor that was involved with the design. So to me, it's an interesting coupling of the contractor for construction and the designer. This shows the resulting cross-section with the design assumptions and drainage tunnel due to concerns of leakage at the base and through the masonry. The uplift shown by the solid line in the diagram below the dam's cross-section was full head water to tailwater assumed by the engineer Halsley. The dashed line shows the assumed uplift by Deacon, who I believe was also a designer, but also a contractor, as the line of drains drops to it at the tailwater. These uplift assumptions are close to what is typically assumed for current dam safety assessments. So we have seen that uplift pressure was sometimes considered in the design of dams, but was not included in the design standard, the profile of equal resistance. So we remember that cross-section of the Vyrnwy Dam with its base 90% of the height. The Bouzet Dam is less massive with a base of about 60% of its height. And the Bouzet Dam failed in 1895, killing 85 people. And interestingly enough, a forensic investigation followed. It concluded the need for a solid foundation, no tensile stresses, and to include uplift's role in the design. And again, a plug for the society. Norman F. Smith wrote a paper on this dam failure in the Construction History Journal, volume 10, 1994. So 20 years later, Wigman's 5th edition comments on the uplift force by stating, quote, some attention should be paid to this force in the case of very seamy foundations, but in most cases, this force will be exerted only a very small area of the base of the dam. Notice it just says a very small base. In his 8th edition in 1927, the consideration of full uplift leads to, quote, The folly of taking such extremes assumptions, close quote, requiring a base as long as a dam's height, which is very similar to what the Belgium engineers assumed. But he calls that a folly. So we go to the St. Francis Dam just a year or two later after he published his book, which was a concrete gravity dam, a new material. It was completed in 26 to a height of 185 feet. At 11:57 on March 12th, in 1928, the dam catastrophically failed, and the resulting flood killed more than 431 people. Uplift pressure played a role in the failure, along with several other design and foundation issues. And the disaster marked the end of the designer Mulholland's career, and that started as a ditch tender for the Los Angeles Water District. And I think this picture, interesting, the main section of the St. Francis Dam was constructed with 10 uplift wells set in 2 rows. And this portion of the dam did not fail, only the sloping abutments, which did not have relief wells or drain wells. One would think that on the base of this photo alone, uplift and drain are critical for the stability of dams would be assumed. So now we go to the granddaddy of them all, Hoover Dam, which we always assumed just was no problems at all. But Hoover Dam, of all dams, also had uplift issues. A grout curtain consisting of just a single line, which we know is substandard today, and only about 125 deep, was installed as they were preparing the foundation. And this depth is only about 20 feet of the dam's height. Interesting also, 4 holes had to be abandoned in the Nevada side due to excessive grout takes. And this is a big red flag when you're talking about foundation for dams. When the reservoir was filling in June 37, excessive seepage flow overwhelmed the lower galleries and excessive uplift pressures were measured against the dam. So a post-construction grouting program was carried out from 38 to 47, and they extended the grout curtain to more than 300 feet below the dam foundation. And this post-grouting program cost almost $4 million, and the original cost of the entire dam was $50 million. So this post-grouting error, or the poor assumption, cost about 10% of the original cost of the dam. And here we finally start getting measurements on uplift pressures on dams. And this is figure 12 from a 1944 book on engineering for dams. And it shows just how the uplift pressure going across the base for 10 dams. Note that 3 dams do not have foundation drains and the location of the drains for other dams. In 3 of the dams reduced the uplift pressure to tailwater, as was assumed in 1880 for the Vernouillet Dam. Also note that for 1 dam, the uplift pressure is greater than theoretically possible. The presence of an upstream grout curtain is not shown. This debate about this potentially large force acting on dams continued for about 75 years. After numerous dam failures, it was concluded that the uplift force plays an essential role in their demise. To me, it is interesting that the initial design assumption is that uplift is small or only acts over a very limited area. Today's design standard is that headwater to tailwater uplift pressure is assumed unless an extensive grout curtain and drainage system is included. And we end at the tallest dam in the United States. The spillway chute failed along with the foundation rock while water was being released down the spillway chute. This failure is related to uplift pressure. In this case, it was hydrodynamic pressure flowing over the concrete slabs. In conclusion, I'm amazed to find out that it took about 75 years or about 2 generations of engineers, designers, and construction, along with dam failures, to reach an understanding of uplift pressure for the design and assessment of dams. With a historical understanding of how uplift pressure was treated, dams that were designed and constructed before about 1950 will likely to assume reduced uplift pressure. This line of history is now what I thought engineers typically follow, and that we usually start with a conservative and refine our design and analysis as we learn more. What path are we following as designers, engineers these days? Are we following, quote, successful designs, or are we learning from and anticipating failure, whether actually experienced or hypothetically imagined. I thank you for your attention and look forward to your questions.
Thank you, Kevin. I'm pleased to probably pipe in that all those Maryland civil engineering students need to solve for W sub U. There'll be a test on that, just so you know. Clifton, any questions?
There's some, yes. I'll just take the first one from the top. It says, when did the engineers develop an accurate equation for uplift pressure?
When, well, I would say it kind of goes dam by dam and foundation by foundation. I would say you basically have to assume with the conservative of headwater to tailwater, and then you literally have to measure it. You make a design assumption and then you construct it and then you measure it to see how close you were. That is very difficult. Like, to me, it's interesting that equation that was presented there that Peter pointed out. There's a lot of variables in there that you basically have to make assumptions or engineering judgment. And we just don't really have a good handle on that still to this day. And it's so variable with the foundations.
Hello. So I'm very excited to talk from the other side, the other continent. I'm talking from Rome, Italy. I'm an architectural historian and a practicing architect. Have been working on archaeology since I was a student, starting with working with the Colosseum, and then expanded my experiences in the Mediterranean. So today, I would like to offer this presentation on brick vaulting. This is a study I have been doing the past 20 years. I think that you know the Pantheon in Rome. It's an extraordinary building that was built in the Roman times. And as you know, the vault is made out of concrete and shows the potentials of using a building technique that was very successful for the Romans, but in some way was not adopted in later construction. When, if you take, for instance, the dome of the Duomo in Florence, it is a brick construction. So the point is, brick construction became, for vaulting and arches, one of the most successful way to address monumental domes. And it's interesting to understand, where does this system of construction origin from? To do that, we have to go we have to go to earlier periods. We have examples, of course, of brick vaulting in the Middle East, much earlier than the Greek and Roman times. But in the Mediterranean, we start to find the use of brick construction and brick vaulting and brick arches in the Hellenistic time. That is to say, between the 4th and the 1st century BCE. It is one of the possibilities that this kind of construction was ideal for building furnaces, that is to say, places where to burn ceramic. And from that, the origin of special bricks resistant to fire were started, and we have many examples, as the one you see here, which is in Sicily, of vaulted construction made with bricks. So actually, it's very interesting to understand where and how this kind of building technique for vaulting started to be adopted in the Mediterranean. And as you know, from the Mediterranean, it expanded then to whole Europe and became, and it still is, one of the systems that is alternative to the use of concrete in construction for vaults. This is an example in central Italy. This is how the ingenuity of builders started to use kind of brick vaulting with without mortar, with this kind of voussoir bricks, that is to say wedge-shaped bricks, in order to give the shape to the vault. Actually, the system adopted for the construction of bricks made use, particularly starting with the Roman period, of mortar as a bonding agent. So the typical thing that you can see is this kind of vault that we can find in Greece. It is parallel to the use of vaults in concrete in Rome, but is completely different in the way it is achieved. You have the centering, that is to say, the element that supports the vault during construction. Then the vault is built. At the moment you put the key brick, the forces start to be diverted to the abutments. And then at this point, you can remove the centering and then build above this, typically in a Roman way, a massive vault made out of mortar rubble. So it looks, the form looks like a concrete vault, like the one you could find in Rome, but actually is built with bricks. The reason for that stands in the fact that the quality of mortar, which is fundamental for a concrete vault, was not possible in other contexts different from Rome and other places around Rome. So in Greece, they developed this kind of building technique, which gradually became very successful, to the point that we find in Greece these very exciting buildings, of course, in ruined condition, which is the positive thing is that we can study the way they are well built, because they are not plastered, and the masonry is visible. Another system that was developed in Rome was imported from the Middle East. These are the so-called pitched or vertical brick vaulting. This is made with a completely different way. The bricks are not placed radially, but are placed as arches, thin arches, as thin as the bricks, that are placed one against the other. The positive thing of this kind of brick vaulting is that you don't need a centering. So you don't need a support to do that, because the first arch is built against the end wall. And so here you have an example of a cistern of the Byzantine period in Athens. This building technique is still adopted in Mesopotamia and Iran. This is a picture that shows how builders can create a vault without using centering. And nowadays we have many exciting examples like this that are documented. There are many builders in Mexico that are doing that. So I connect, of course, to the Mexico lecture, because in Mexico, actually, there is a very strong, in some areas, there are the masons that are still adopting kind of traditional build construction. And so this is very important to go back and learn about these building techniques, because they have very strong potentials today, especially with the challenges we have, for instance, with climate change, and we have to find building techniques that are more resilient. And so for this reason, we have to go back to the experience gained in the past and in the traditions. This is the same mausoleum we saw earlier. And here we see the use of this kind of pitched brick vaulting, which is adopted for the upper part of the dome. So in Greece, they developed this kind of two ways of building, radially or vertical brick vaulting. Actually, the masons were concerned about minimizing centering, because it's a matter of making more quicker the construction, more economical. And for this reason, brick vaulting became particularly successful in the Roman Empire, except from Rome. But from Greece, it went to Asia Minor, and from Asia Minor, it was adopted in Byzantine architecture. And the Byzantines, they exported that to Italy and Spain. And from that moment, we can more or less follow the expansion of brick construction all through Europe. So brick vaulting became so incredibly successful in Europe. Now, the last step of this presentation will be something different. What comes after? What can you do? You can do that the vertical brick vaulting without centering. You can do radial brick vaulting with centering. But then, at a certain point, there was it happened in Marrakesh. At least I am proposing today this building, which is absolutely outstanding, placed in Marrakesh as the first building using a new kind of vaulting technique, which is the so-called tile vault. Here you have some pictures showing that this building has an exterior dome, which is made traditionally with a vertical, with a radial brick vaulting. And then you have inside, protected from the exterior vault, a very particular vault. You see here, this vault is placed on these timber brackets. There is a stone which is placed above to stabilize the bracket. And then you have these ribs that are built on the bracket. This is absolutely unique, outstanding. And the understanding of this kind of vault is very difficult if we don't consider that it comes from, the experience comes from other regions, as we will see. The point is that between the ribs, you have these bricks that are create a tile vault, that is to say, a very thin vault, which is as thick as the brick. The origin of that comes from Persia. There are examples of this, and the very difference from the other vaults we have examined is in the use of a different bonding agent. These tile vaults, and here you have an example, the first example documented of tile vault in southern Spain, some 80 years after Marrakesh. They use gypsum as a bonding agent. So gypsum sets very quickly, so makes it possible to stick very rapidly the bricks one against the other. And doesn't use centering, so it's ideal. And it's an incredible lightweight construction. So has all the ingredients to become a very successful brick vaulting. And then it is fire resistant. For this reason, it became particularly successful in the United States, thanks to Guastavino, who imported that in late 19th century to America, and made the Guastavino Vaulting Company, which built some of the most extraordinary tile vaults, which have been studied by John Oxendorf, and which many were demolished, but many, as the one you see here in Ellis Island, are still preserved. So you see that brick vaulting has many potentials, but is also something that should be included more into present day construction. Thank you.
Thank you. Paul, I have a question. I haven't received any questions from the audience yet. In terms of the advantages and disadvantages of radial versus vertical, once the advantages of vertical vaults were realized, not using centering, what were some reasons to continue to utilize radial vaulting? Is there a performance difference between the two in the long run that is recognized, or is it just maybe because, yeah, I'm not sure, looking for maybe that motives to use one or the other?
The main discriminant is the span of the vault.
Okay.
Vertical brick vaulting typically is used for vaults up to 5-6 meter span. Exceptionally, we have in getting up to 11. But when you come to huge vaults, as the domes, for instance, used for the cathedrals, you have to go to radial brick vaulting. Also because it's easier to build a thicker vault rather than vertical brick. Because vertical brick is, if you want a thicker vault, you have to do, as in Egypt they used to do, more arches one above the other, which do not connect one to the other. With radial brick vaulting is much easier to make one whole structure, so it's more resistant.
Thank you very much. And now we have a question from the audience that is in a similar vein in respect to why use a system or not in a particular situation. I think no one presented this. Sometimes we're not getting everybody's name. No one says why was brick vaulting successful in the Roman Empire, meaning outside of Rome, but not in Rome itself?
Rome had this tradition of using this hydraulic mortar, which was experimented in the period that goes between the 1st century BCE and the 1st century CE, when they succeeded to do something extraordinarily strong. Consider that the Dome of the Pantheon is 45 meters and is unreinforced concrete. Today, we are not able to do such a massive dome and huge dome without using iron. So the secret is in the capacity to create a very strong mortar, which made it possible to realize, to build the huge vaults in Rome. But bricks, indeed, they were used, but in very extreme cases. We have solid brick vaulting used in the Pantheon, but not in the dome, but in the supporting walls, in the drum. The drum is made like an aqueduct, is made of bridges, and these arches are made of solid bricks. You have similarly in the Baths of Caracalla, but then the Romans started to adopt a different solution. They started to insert brick ribs into concrete. So they used the capacity of bricks to create a stiffer structure, but with concrete. They never abandoned concrete because it was good for the materials they could find in Rome and was absolutely very strong.
Oh, you're on mute, Clifton.
Thank you. I'd like to get a couple more questions for Paolo and then go back to our other panelists. This next question is related to the Gustavino vaulting. The question is this vaulting also based on gypsum mortar?
A good question, thank you. Actually, nowadays I am building tile vaults. I do, in my projects are based on using tile vaults with masons coming from Valencia. And they are very experienced. They still use this technique particularly for building staircases because it's very quick, very economic. And so the first layer is made with gypsum, and then they use a second and third layer depending on the typology of vault, which are made with cement mortar.
Thank you very much. And then one more question before we rotate. When was non-centering vaulting invented? What country and how did it migrate to Mexico, where it is still quite popular? I think you've already addressed the first one, but it might be helpful to revisit that in the context of this question.
The use of the centering is when it starts is kind of question. Brick vaulting starts in the Middle East, Mesopotamia, and Egypt. We have traces of very of supports for these vaults. So we don't know exactly when they started to avoid, but they were small vaults. So the idea when you do a big vault, and you, of course, you need a centering, a support. So I cannot answer with something very specific. We actually, we are presenting in next year in Lisbon, there will be the Construction History International Conference, and there will be one of the panels will be on vaulting without centering, and I will participate. So there, hopefully someone will come with a solution. The other, then the second part of the question was about?
The connection to Mexico. And I'm looking.
Oh yeah, but Mexico, this kind of vaulting depends very much on a tradition that is interrupted by modernism or not. In some particular contexts, which remain very strongly connected to tradition, sometimes for economical reasons or isolated, could be one of the means. Another means is for practical reasons, as in Valencia, where they build the staircases. But in most of the cases are very good masons who have learned, they had the opportunity to learn this vaulting, and they have decided to adopt that. I know many cases of this, but for instance, in Rome, we tried to propose the construction of a tile vault to the civil engineer department who approves structural design, and they refused that because they could not understand a structure that has been being built in Rome up to 40 years ago. There were plenty of these tile vaults in Rome, and nowadays there is no person able to do that. So when you break a tradition, you lose how to do that. So what you have to do is to reinsert this tradition. We do that normally through conservation projects. Conservation projects are always a good means to restart a tradition that has been broken by modernism.
Thank you, Paolo. There's a question for Rebecca. And the question is, what do you think the use of traditional materials, or do you think the use of traditional materials fell into disuse in, and I'm mispronouncing the town, so I won't even try, because of the local natural resources, because the local natural resources were not or could not be sustainably managed? Or were there other reasons why these materials were supplanted?
That's a good question. I definitely think the root of the problem doesn't lie in the materials themselves. I think the broader narrative of concrete as being a superior building material far outweighs the environmental conditions for its disappearance. But I guess the point I'm trying to make is that once you make that decision, the original reason that you decided to switch kind of gets into this reinforcing cycle with the environment, where the two are feeding off each other to the degree that the former building techniques then become I mean, Paolo was also kind of talking a little bit about this just now, but the former techniques become even harder to use because the materials disappear. So yeah, I don't think the original reason for that happening was material, but it's becoming almost impossible to use those techniques now for material reasons, among others. There's so many reasons, but.
Thank you. I have a question for you, Rebecca.
Sure.
In your slides and in your talk, you introduced this, the wood construction where the trees were milled by hand and then laid in a manner that's reminiscent of considered log cabin building, which is a very inefficient structural material method for building. My understanding from reading about vernacular construction is that that technique came from Scandinavia and was carried over to the North America. Is that the genealogy of this technique, or is it a different origin?
I wish I knew, and I have been so curious about that. I've been researching that a lot, actually, to try to get to the bottom of it, and I still don't know. It's the region where that's prevalent has a lot of sort of missionary activity historically, and I know that's a big way that it was disseminated, for instance, in the United States, like in the 19th century. So I'm starting to hypothesize that maybe it's related to that. There's a chance it's endemic to there, but I think it was likely imported, but it's been there for at least 150 years. So that's a good question, and I wish I knew the answer.
I'm going to keep a tab on you to see when if that answer is coming. I look forward to it. Thank you. A lighthearted question for Kevin. What is your favorite dam?
I typed that, and I have to go with Hoover Dam, but it's tainted by that. I got to tour it before 9/11 in the good old days. They would take you down, you would ride in this elevator and take you down to the base, and you would go upside, and then you would look up at this 700-foot wall of concrete. And you think, boy, I hope that thing doesn't fail right now. That would be bad if it did. So, and I guess the double bonus now is if you go to the Hoover Dam, there's an amazing bridge just downstream of it now. So it's kind of a double bonus now. You get a bridge and a dam for the price of one admittance.
Great, thanks. I appreciate the fact that you're suggesting that we should, not necessarily look at the finished result and the fact that these are heroic efforts, but that there was a learning process and there needs to be a continual learning process. So my reverence for that dam, and I visited it before these changes happened, still remains even after understanding that there was a huge change order involved, which could be then in itself, a reason to be critical there. So a question, related to dam use is from the audience is, with many dams planning to be removed as they are no longer in use, what are your thoughts on the direction of future dam use in the country? I think this is a broad question in respect to our optimism and the sentiment with respect to dams in this country.
Right, I think, yeah, it's just what was the original intent of the dams? And early on, like even into the medieval time, it was water power is a really great source of energy for the start of the Industrial Revolution. And that carries on basically until it's efficient to make electricity through other means, through steam, basically in the 1920s. So a lot of these old mill dams are very prevalent in the East. Yeah, they have just kind of outlived their purpose. Mm-hmm. And yes, they are slowly coming down. But dams do still, a lot of dams still do serve their purpose. But it's a huge debate, and it's still raging on, especially in the Northwest with the fisheries issue. There's all sorts of issues related to dams, and it's a very emotional, I would say, issue as well.
Kevin, is there also the dams being considered also for sediment control? I mean,
well, right, yeah,
water quality issues. Water quality issues.
Also, you get the sediment control, and then you get the dams that just trapped all the sediment, and then during the industrial area, these sediments become contaminated. And now, how do you deal with all these contaminated sediments? If you do bring down the dam, and that becomes a very expensive issue to deal with. So yeah, the sediments. To me, the most interesting sediment dam was the one built out in below Mount St. Helens to try to control the sediment coming down some of the water runoff from after the volcano blew.
Thank you, Peter. Kevin. Here's a question for Paolo about the dome in Marrakesh. And the question is the inner dome supported only on timber, or was that for construction and later supported on masonry?
No, it's the inner dome is supported by these timber brackets. It's absolutely astonishing for our concept of construction, but it's like this.
Yeah.
I have not seen that personally, but there is a publication made by the French equipe which made the restoration, and they actually broke the exterior vault to enter inside the cavity, and so that because from the inside, from the introdos, you don't see anything.
Thank you very much. It's absolutely fascinating. Anecdotally, I am surprised how much wood structural construction is interjected into masonry construction, even in our basic houses where I live. Another question about so there's a question about the domes too. Is non-centering vaulting the same technique rediscovered in modern times by famous modern Egyptian architect Hassam Fadi?
Yes, Hassam Fadi, he was the one who pursued the idea of revitalizing traditional architecture for his project was idealistic, some way failed, but he was using exactly these techniques, the vertical and the pitch brick vaulting. So it is something that is still in use nowadays in some regions, although I have been working in Cyprus for many years. And since the first time I was there, I was saying, why are you building with concrete when all the traditional houses were made with pisé, and it was the right way to isolate from the heat. You have so hot weather, and you do this kind of modernist design, and then you have to use air conditioning, and you waste energy, and so on and so forth. So it's a matter that I think that I take the opportunity to send a message that I always send, is that we are living now a moment that we have to rethink. We have to rethink because the challenge we have from climate change urges us to use local materials, local building techniques, to go back to create a building environment with more identity. And so revitalizing this kind of traditional building techniques becomes not only positive, but a necessity.
Thank you. I'm going to slip a question from myself, and this has to do with the thin tile vaulting. You've illustrated it as part of an interior dome system. So it's the lining on the inside, and there's a superstructure above. Are there any examples of this thin vaulting where that is the primary envelope for the building, or is it always a interior application?
This is quite usual in Islamic architecture, although many times the exterior envelope is made of timber, is a timber roof. And there are many cases like this. I was in the Mosque of Cordoba visiting 1 year ago, and originally these vaults that are from the 9th, 10th century, which are not tile vaults but are traditional stone masonry vaults, they were protected by a roof, a timber roof. But in restorations that occurred centuries later, they made a tile vault to protect the masonry, stone masonry vault. So the double shell is one thing that is, as for instance, St. Peter in Rome, or the dome of we saw from Florence is a double shell dome. So the two shells, they work together. There are structure, the structure is made out of the two shells. But in these Islamic vaults, the two shells are independent. One protects the other. And so there are examples, although is not very much used.
Thank you. There's a housekeeping question here, Peter, and I want to bring it to attention before this individual leaves. And the question is, will the proceedings or a transcript thereof be archived? Somehow this question was canceled before. Apologies if that happened. Can you tell us about where people can find?
Yeah, so I will,
this record?
yeah, and just as a way of sort of working into our closure, we are planning to record, we are going to record this, and we are going to host this on our construction history website when it's been edited and properly attended to, shall we say. And all of the participants today, and as well as those that have registered, will be getting an email with a link to that YouTube video when we have it uploaded. So that's one of the benefits that we get. So I think we've pretty much exhausted our questions right now. I do want to thank everybody, my panelists, for participating, as well as all of the folks here on this webinar. Take note of some upcoming CHSA events. Next spring, we plan to host a similar seminar with the 3 topics noted there that you see: machines for selling, introduction to the rolled I-beam, and a preservation project here in Minneapolis, as well as, hopefully, COVID may prevent this, having our actual annual meeting coming up here in June 4th through 5th of 2021. And of course, we welcome all of you to become members of the Construction History Society so that we can continue to share all these wonderful stories of the past. So with that, again, panelists, thank you very much. Paolo, thanks for staying up past your dinner time in Rome. And we look forward to conversing with you all again in the future. So thank you. And I think at this point we can sign off.
Bye-bye.
Bye.
Bye-bye, everybody.